This video is going to be a bit of a mix-mash between all of the calculus topics, namely differentiation, applications of diff, integration, and applications of integration. So we're going to go through the Cambridge Unit 3 and 4 book, go through that Chapter 12 review section, and just do some questions. Enjoy. Okay, so this one is going to be a full calculus review, essentially. So we're just going to go through the chapter review covering chapters 9 and 11. So that's going to be some derivative stuff. It's going to be applications of derivative. So tangent lines, stationary points, maybe some Newton's method, although probably not in the tech free. And then the integration side of things, all the anti-diffs, all that sort of thing. So I think the way this will work well is if I introduce each question individually and we just sort of workshop them together as we go through it. So first things first, probably get the screen share going. That'll be a good idea. Okay, screen share is up, camera's up, cool. All right, so first up, we've got a function y is a division of two polynomials, and I want to find the derivative of that. So I'll start by writing that out. In the meanwhile, have a think. There's a few things you have to ask yourself when finding the derivative of any function. I'll start by just writing it out first, and I'll begin explaining. It's got our x squared minus 1. We've got our x to the power of 4 minus 1. So one of the first questions you have to ask every time you're doing the derivative of any function is which of the three main rules apply, whether it be quotient rule, chain rule, or product rule. So what I'll do is I'll get up what each of those look like and each of the scenarios for which you would use them. Let's see here. Derivative techniques. Because it's never going to be quite as simple as just you found the thing that you want to find the derivative of directly on the table. So the first thing, or the first possible rule, would be chain rule. So you would use chain rule for composite functions, essentially. So the example I give is f of x is natural log of x squared. You have a function inside of a function. The second possibility is product rule, where you have a multiplication of two separate functions. In this case, it's x squared and sine x. There's a multiply between those two functions. And then the last is quotient rule. You have a divide of two functions. In this case, it's natural log of x divided by x squared. So based on what we're seeing from those three main rules, which seems most applicable to the function that we have? Chain rule, okay. So chain rule is for composite functions. So what part of this do you see as a composite function?
Chris, I was meant to write question rule.
Meant to write quotient rule? Yep, no worries.
Yeah.
Yeah, so quotient rule, still same question then. Why is it quotient rule?
You've got a division of two functions.
Yeah, division of two functions, precisely. You got a division of x squared minus 1, and that's being divided by x to the power of 4 minus 1. And so yeah, what we're going to fundamentally do is do our quotient rule, which means we need to find the derivative. Well, first we're going to define our functions. We need to define what u is and what v is. What's what in this case? You can have a look at the screen share to help you out. There's a written example and there's also a generic example. Because u and v have to be very specific things. In the product rule, it doesn't matter which one you call u and which one you call v. In the quotient rule, it does matter.
X squared minus 1 is u, and then x to the power 4 minus 1 is v.
Yeah, correct. So the u always has to be the numerator, the v always has to be the denominator. So, as you said, u equals x squared minus 1, v equals x to the power 4 minus 1. From there, we have to find u dash and v dash, the derivatives of each of those. What are the derivatives? I've got up a table of derivatives if you want to refer to those on the screen share. Uh, 2x and 4x power 3. Yeah, both of those are correct. So this is all the whole power down the front, reduce it by 1 situation. So the 2 comes down the front, makes it x power 1, so you just leave it. And then 4 comes out the front, x, and then 4 goes down to just being 3. Both of those constants, derivative of any constant always goes to 0. That's why those disappear. That's pretty much it now. So now we just plug in exactly what we see in the quotient rule. So if you have a look at the screen share, you'll notice that it's vu dash and then minus uv dash, all divided by v squared. We have all those terms, so we're just going to plug them in accordingly. The way, if you lay it out this way, it's pretty much always a cross multiply. So you do your v, then your u dash, but in this case it's going to be a subtraction rather than an addition as you would do for product rule. So we got our vu dash, that's going to be, might use some road for no reason, 2x out the front of x power 4 minus 1, and then minus, you could say, 4x cubed out the front of x squared minus 1. And that all divided by v squared. Now, it's worth highlighting. This v, there's no way that that's going to help us with factorization or simplifying things down anymore. And so what I like to do to simplify or reduce the amount of effort of rewriting this thing over and over again, I will just leave it as v squared on the bottom and then only put it back in at the end. From here, you have a couple of options. You either fully expand or fully factorize. One of the things you could do to factorize would be take a common factor of x out the front, although just sort of looking at it, it doesn't look like that'd be all that nice. If you just took a common factor of x out of here, you still got an x squared, and it almost makes it more complicated than otherwise. So best bet would be to expand in this case. So 2x into x to the power 4 gives us 2x to the 5 minus 2x minus, now use big brackets here, that way, well, maybe not actually. Yeah, maybe don't use big brackets. Minus 4x cubed and x squared make minus 4x5, and then minus 4x cubed, they cancel down to positive 4x cubed, once again all over v squared. And then from there, well, we just do a bit of collecting like terms. Minus 4x5 and 2x5 make minus 2x5. We've got a positive 4x cubed, we've got a minus 2x, and then at this stage, because our numerator is fully simplified, I would now bother to put the v squared back in as what it should be. X power 4 minus 1, x power, let's try that again. X power 4 minus 1, and then all of that is squared. You can leave that as is. This is perfectly fine. That's pretty much it. So we've just found dy on dx. So what you would probably be doing, if you were to be very accurate with your working out, is at each stage here you'd say dy on dx equals all of these. Now very specifically you would use dy on dx because that's what the question has asked you to use. Even though f dash x is equivalent notation, you should use whatever's told to you in the question. Although, oddly enough, I did see an exam report from VCAR which didn't seem to care very much about that at all, which was interesting. But it definitely makes your answer look more favourable. Anything to clarify there? If not, start having a think about part B, which is find dy on dx equals 0. How might we go about that? Dy on dx equals 0. If this is dy on dx, then it just means this whole fraction equals 0. How might you go about solving that?
You would make like the derivative equation equal to 0 and then solve for x.
Yeah, precisely. So yeah, you would absolutely just slap a 0 where this dy on dx is. The question now becomes how do I actually solve that? What would be the first line after putting a 0 here?
I guess if you take like the denominator and then you put it to the other side,
Yeah.
and yeah.
Yeah, exactly right. Whenever you have a fraction that equals 0, the denominator doesn't actually contribute anything to it. Um, it is worth pointing out you do want to have a look at your function and consider any divide by 0 errors before that. Not because of the flip over. Every time you multiply by something, you can do that just fine. It's just that you want to consider that if you ever get a solution x equals 1, you have to ignore that. Because if you were to put x equals 1 in here, denominator goes to 0 and the whole thing would go to 0. So before we do anything, we would say x does not equal 1, and we'll just keep that in the back of our minds in case that's relevant. But yeah, absolutely. Multiply both sides by that, gives you 0 equals minus 2x5 plus 4x3 minus 2x. Yeah, much easier. This is now a polynomial. So what comes to mind when solving polynomials equal 0?
Factorization.
Factorization, yeah. Any easy factorizations you see here?
You can take minus 2x as common.
Yep, we can take minus 2x out the front. So you got minus, oops, you got minus 2x out the front of, this will now become positive x4. This will become negative 2x squared. This will become positive 1. Sounds about right. What else?
I assume like, for the x to the power of 4, like, polynomial, you would use as for that.
Well, CAS will definitely work, although I will say this is in the tech-free section, so there's a tech-free way of doing this. But yeah, so you're right in the sense that you're separating these two terms and you're doing a null factor law on them. So yeah, this one's going to give you the x equals 0 solution. So we know that definitely exists. And then you're like, okay, well, we got this x4 minus 2x squared plus 1 equals 0. And that's a bit of a pain because we're not seeing any easy factorizations to make that work. There is one technique I think that seems like it could be doable here.
Yeah, I think I know.
Yeah, what's
So
going on?
we could make like we could substitute. So make like something maybe like let's just say a equal to like x squared.
Yeah,
Yeah.
really good. Capital A. So x squared. If a is x squared, then x4 is now the same thing as a squared minus 2a plus 1, and that's a lot easier to solve. Yeah. So you can solve this however you like now. It's a quadratic. You could factorize it. You could quadratic formula it. You could even complete the square if you really wanted to, but maybe not. Yeah. What should we do?
We can see that's like it's going to factorize to a minus 1 squared.
Yeah, a minus 1 squared. You got minus 1 and minus 1 makes positive 1, and then the addition of those two numbers gives you the minus 2. So capital A minus 1, capital A minus 1, or you can just write that as a minus 1 all squared. Yeah, that's good. And then from here, well, there's really not much else to talk about on this one. You would square root both sides, gives you a minus 1 equals 0, a equals, whoops, not 0, but 1. And then when you have capital A equals 1, what do you do once you have that?
You solve the x squared back in.
Yeah, we know that a was x squared, and so now we have x squared equals 1, which has two possible solutions, x equals plus or minus 1. Is that all good, or have I done something weird there?
That's all good.
Incorrect. There is something weird here. At the very beginning, we
Okay.
said that x could not be 1. And so when I say x is plus minus 1, I in fact say, nah, can't have that. This one's bad. X equals minus 1 and x equals 0 are the only actual solutions for this. Um, yeah, that's all. So this thing definitely worth considering. It always, like, a lot of the time, you have to sort of pay attention to any potential discontinuities on the graph, of which x equals 1 is in fact a discontinuity. That's one of the disadvantages of multiplying both sides by denominator. When that's completely out of mind, it can be kind of hard to remember that that's still a factor as far as solutions are concerned. Cool. All right, that's that one then. The rest of this is just some more fundamental derivative stuff. We won't go into much detail unless you want to, so I'll just write them out and we'll talk about how we would go about it. So question 2 is y equals 3x squared minus 4x all to the power of 4, and we want to find dy on dx. So again, first question you want to ask yourself is this a chain rule, product rule, or quotient rule scenario? Yeah, that's the question. Which one would we use? Chain rule. Yeah, correct, Pierre. So we've got chain rule. We use chain rule for composite functions. Why? Yeah, how would I start the chain rule on this one? What would I actually do? Because it's one thing to know it's chain rule, it's another thing to know how to then do the correct substitution. What do I sub in my letter as being? U to the power, yeah, u to the power of 4, correct. So the letter u is going to replace all of this. You say u equals that gives you u to the power of 4, and then you take it from there. If anyone wants to see that done in full detail, let me know. Otherwise, I'll write out the second one and we can have a chat about how we would do that. I guess I said f of x instead. They said f of x and they said find f dash. So again, what kind of a trick question here actually. What type of rule applies?
It's like both product rule and chain rule.
Yeah, correct. So product rule because you've got a multiplication of two things here. But when you define this as your v or your u, finding v dash or u dash, whatever this is, that's a chain rule. Or at least it's technically a chain rule, just because it's, even though this does simplify down to just the 1 over x as normal, you still do, you're implied as doing the chain rule for that. Yeah, that's about it there. Cool. What else we got? 4a. We got another function, tangent to f at x equals b, passes through point, find b. Alright, so that's fairly involved. Nice. I'll write down the key information there. So we got the function, e to the 2x plus 1. It's sometimes worth like considering, like literally write out the domain of your function. We saw an issue where that was an issue earlier if we didn't write that down ahead of time. So it can pay off ahead of time to be like, hey, look, what's my actual effective domain in here? Because a lot of the times the exam will be like, hey, this doesn't actually have a full maximal domain. So you got to keep that in mind when it comes out to it. But okay, so we've got our function, and then we're told tangent at x equals b passes the origin 0, 0. And we have to figure out what b is based on that. So it's mentioned tangents already. What kind of things become important when trying to find tangents? Or just any question that has tangents in them?
Wait, sorry, could you repeat the question, please?
Yeah, so the question was, because tangent is like the key word that's been mentioned in this question, what kinds of things become important when the question starts talking about tangents? What kinds of things do we usually have to solve for? Yep, derivative or gradient. Yep, correct. Both of those are important. We're doing tangent lines, and so derivative is pretty much always required for anything tangent line related. So if we were to try to find the derivative of our function f dash x, either tell me what rule would be required or just tell me the final answer. What would f dash x be all about? I'll leave the table of derivatives up on the screen share.
Grace, does the derivative just remain the same?
Kind of. It remains the same for the basic exponential, but we don't quite have the basic exponential here. It's pretty close to it. The fact that the power is 2x plus 1 means we have to do a special rule for it. P has got it. Do you know what rule she had to use there?
Chain rule?
Chain rule, yeah. It's a composite function. So derivative of top is 2, and that comes out the front. So it becomes 2e 2x plus 1. You can rewrite domain on this if you want. It's up to you if you want to have that reminder. But okay, derivative, right? So as was said before, derivative is all about gradient, right? And so when you think about tangent lines in general, they are y equals mx plus c. They're just some linear in there. And if you want to find a tangent line, you need to know what m is and you need to know what c is. Those are the overall things that are required there. There is some information we can get pretty much immediately based on what we have already. What do you think we can get? We can get either m or c. Just depends on which one you see first.
Yeah, if the tangent passes through like zero, the origin, that means like there's no C.
Yeah, correct. If you sub in x equals 0, y equals 0, the m disappears, and therefore c equals 0. So really we're just now down to y equals mx. Sweet. That's cool. Our goal, so now we've got an m that's unknown, and if you, maybe I didn't explain it, but our goal is to figure out what b is. So we've got this equation y equals mx, m being the gradient. How do you think we could start rewriting it instead of just being m, working our way closer and closer to getting something with b in it? The hint is that derivative and gradient are closely related to each other. Derivative is kind of like the function that tells you all possible gradients of the function, but we want a very specific gradient. We want the gradient of the linear. Reminder that the linear is taken at x equals b. So it's basically as if, yeah, maybe even we could even draw a quick graph of it. So e to the 2x plus 1 would look roughly like this. And for the tangent to pass 0, 0, it would basically have to do something like this there. So this spot here is b, whatever that is. Maybe use that picture to see if that rings any bells, how you might start rewriting m.
Wait, so then technically, like, couldn't B be anything? Like, just as long as the tangent, like, crosses like 0, 0, then couldn't B basically be anything?
It could be anything, any one specific thing though. Because if I took it anywhere right or left of this specific spot, it wouldn't cut the origin. Like if I took the tangent line out here, for instance, it would cut down there. So it could be any one thing, but it's this specific thing, whatever that is. But yeah, the thing I'm looking for here is using f dash x. So if I wanted to find the gradient at any point on this red line, what I could do is I could sub in a specific x value that I know into my derivative, and that will give me the gradient at that spot. The key thing to consider here is that the gradient of the tangent line is the same thing as the gradient of the function at that spot. So if I sub in x equals b into my derivative equation, I get the gradient at x equals b for the red line, but also for the green line. So when I do my f dash of b is 2e 2b plus 1, that is the gradient at this spot. So all I do now is, if that's m, because m is the gradient of the linear, I now have y equals 2e 2b plus 1. 2b plus 1, and then there's the x out the front there. And that would be the equation of the linear there. Now our goal is to figure out how to get b out of this, which now that I'm looking at it is pretty interesting, because if you just sub in 0, 0, the whole thing disappears. So we're not fully out of the woods yet. There is one other point that's not necessarily told to us, but is implied. If we can't use the 0, 0, the origin, what other point do we know exists on the linear? Oh, whoops, that's a highlighter. We could actually find that point.
Point B.
Say again, sorry?
Point B.
Yeah, point B. Now that's just an x value, by the way. And so to get the full point there, you would just do the coordinate b, comma, f of b. That is a point we know exists. And so f of b would just be our y value, so e to the 2b plus 1 on this right-hand side, e to the 2b plus 1, and then our x value is just b. So we got 2e 2b plus 1, and then multiplied again by b. That gets us a full expression purely in terms of b, which we can then solve for b. So all I've done is that y value there is f of b, that x value there is b, and then the gradient, well, we've already had that. Yeah, and then from here you just do some simplification. If you divide both sides by e to the 2b plus 1, that is a common factor, so they can cancel out, giving you 1 equals 2b. You've got the 2 here and the b there. B is therefore a half. So the only spot you could take a tangent line on this such that it cuts to the origin would be at the value b equals a half, or you could even say specifically the x value of a half, although it does say find b, so you would give it as b as a half. That was a sharp increase in difficulty. But fundamentally, as long as you follow the basic rules of tangent lines, even if you don't know where you're going, immediately just grab your derivative and then start subbing in some stuff, right? Like you got 0, 0, that's a point that's known. It's a point that's known on the original curve and the linear, and so you could plug it into both spots. So even if you don't really know where it's going, just start creating the sort of framework that you already follow for tangent lines, and then just keep going until you just sort of realize, oh, I've actually got a fair bit of information to work with now. But yeah, that's how we go about that one. Anything left to clarify there? Okay. Part B is a very similar question. I think I'll just leave that. It chucks a plus k that's involved in there, which just means it's now applying a vertical translation to it. So you can imagine in the picture that we had, you're just shifting the red line up, and then it would make sense that where you take the tangent line would have to be closer and closer to the origin as this gets further and further up. Because if I drew this red line all the way up here, I mean, you know, it might just be that my picture's a bit off, but I don't know, how close was that? Maybe it is the same spot every time. That'd be a kind of interesting... No, surely not. I think I'm just drawing my picture not to scale. Point being, very similar, and so we'll just leave that one there. Question 5, y equals mx plus 8 is tangent. Yeah, it's the same idea. Part 6 is more of a remembering sort of situation. It says find the average value of a function over an interval. I'll start writing that out. So we have f of x is 1 over 3x plus 1, and we're doing it over the domain 0 to 2. We want to find the average value from 0 to 2. Average value is a keyword. It means a very specific thing. Does anyone remember what it means?
Average rate of change.
Not quite, actually. Sounds very similar, but it's not. Average rate of change would be like the average gradient. That means that you have, let's say you have some curve that looks like this. You have 2 points on that curve. Average rate of change means drawing the slope between those 2 points. Average value means you're figuring out between these 2 points, there's some y value to dip below, there's some that dip above. You want to find like roughly the middle, which would be, if I were to eyeball it, around there, the middle between like here and here. It's the average of all these y values. That's what it means. As far as how you go ahead and calculate that, it's a very specific equation. So I've got that on the screen share up now. Fundamentally, all you do is you find the definite integral over whatever domain you've got, and then you divide that by whatever the length of that domain is. That's all that equation says. So your b and your a value just means the upper and lower bound, respectively. So you got a, let's do that in red. You got a here, you got b here, and then obviously f of x there. So the goal is we want to find 1 over b minus a, so 2 minus 0, 2, that's the length of our domain, times the integral from 0 to 2 of 1 over 3x plus 1. That's what average value, well, that's how it's calculated. As far as what it means, it'll be whatever this y value was here. Now, obviously, this is a quadratic, not a hyperbola, but point being, yeah, that's what we're fundamentally doing. So the question now becomes, how do we evaluate definite integrals? Well, the first thing we do is anti-differentiate what we have. So I'll get up the table of antiderivatives. Or if someone can answer it before that, then by all means. Although this is one of the tougher ones for sure. Alright, I've got that table up. Based on that, what's the antidiff going to be?
Is it 3 natural log 1 over 3x plus 1?
3x plus 1, like that?
Yeah. Oh, and then we have to times half with it.
Times half. Y times half?
Because half is like resting outside of the. Half is outside.
Oh, yeah, this one. Okay. No, fair enough. You could. It's usually easier to just leave this out because what we're looking at is the integral of just this. And then we're going to multiply it at the end by a half. So this integral isn't this. This is only step 1 of that. So really what it would look like is a half. Hang on, say again. A half times capital F of 2 minus capital F of 0. So the half, you could put it in here. Obviously, it just distributes anyway. So either is up to you. I will say though, this is a little bit off as far as antiderivatives go. So the rule for how you handle this one here is this is where you have 1 over ax plus b. There you got 1 over some linear. And if we look at the screen share, 1 over ax plus b is this dot point here. And so what we find is that whatever the a value is comes out the front as a division, and whatever the linear was on the bottom is the linear inside the brackets of that logarithm. Now you can use these vertical lines if you want, although because we already know our domain is entirely positive, we're doing it from 0 to 2, you can actually use these rounded brackets and still be correct. Although I find this will just be easiest because that way you don't have to think very hard at all. It's just those lines and that's it. So in this case, our a value is 3 since that's the coefficient on the x. That means we have 1 over that value. And then all we had to do was knock off this 1 over because it's just the linear that goes in there. Otherwise, everything else is fine. Is it fair enough what we had to do it that way?
Yeah.
Sweet. By the way, most complicated antiderivative. You can see I've got 2 bullet points and then 2 sub-bullet points for one single type of function, a hyperbola, versus everything else is just 1 because it's nice and easy. Maybe just for fun, I'll talk a bit about why it's weird. I don't think this was written by the time we did the class last time, so this might be new for some of you, that or I've misremembered. One of the problems that comes about, if we look at the screen share, one of the problems that comes up is when you're doing the antidiff of a hyperbola, it becomes a logarithm, but hyperbolas are defined for all real numbers, whereas logarithms are only defined for where the bracket is positive. So that's an issue, right? You only have one particular domain that can exist for that logarithm. And so you come across 2 scenarios, which is one case where the logarithm is defined for the positive values, and then you slap a negative on it so that it becomes defined for the negative values. You have to have 2 separate parts that make up the whole antiderivative. That's one of the main problems, which is why there's 2 separate antiderivatives for each domain. So you can get around that by just saying absolute value, which is those vertical lines there, which simply means it doesn't matter if x is positive or negative, we're just going to treat it as if it was positive. That's what that means. The second problem is why we have to have a separate dot point here. Is it worth getting into? This is a bit more involved. I think I'll leave this just for further reading if you would like to understand why it is the case that these have some separate antiderivatives. It's not super important to know why, but more so just know that they are different. The main problem that comes about is 1 over ax, the ax doesn't appear in here, whereas ax plus b, the ax plus b does appear in here. And that might seem like it's an inconsistency. It's not. It's intended. And so this explanation here is there to explain why that's the case. But if you don't really care why, if you just care that, then you can just use those 2 dark bullet points. And I have a whole thing on like an appendix at the back here to say, hey, look, here's what you do if there's no domain. Here's positive domain. Here's negative domain. I've got 6 examples covering all the scenarios if you would like to deeper explore what's going on with this hyperbola. But enough about that. All we have to do is finish up, right? Which is if we're doing our definite integral, remember we're trying to do average value here, we have our capital F of x, and then all we're going to do is capital F of top minus capital F of bottom. So 2 and 0. The half can come out the front, or you can put it in here. Doesn't matter which way you do it. 1 over 3 natural log of 3 times 2 plus 1. We usually ignore the c's entirely because every time you do definite integrals, the c's will cancel out no matter what anyway. So what you'll find is that they don't actually even have it in there as a line of working. And then yeah, all we do is we sub in our x equals 0. Yeah, because it's capital F of the top one minus capital F of the bottom one. And simplify. So going to have our half from before. 3 and 2 make 6, and then 1 is 7. A third, natural log 7, minus a third, natural log 1. Do I... Yeah, we've got a couple of options here. Up to you. How shall we simplify this further?
A natural log of 1 would just mean that it's 0, right? So,
Yep.
yeah. So
Yeah.
the whole thing would be equal to 0.
Yeah, precisely. Whole thing's that whole thing's equal to 0.
Yeah.
And then yeah, you got your 1 over 6 natural log 7 after that by bringing in that half. The alternative is if you didn't see this, you could do your division law. So you could do natural log of 7 divided by 1, but obviously that still just cancels it out anyway. And so you get back to where you started, basically. Or at least you get back to this pretty quickly. And then yeah, that becomes, well, let's see, is that final answer? We already put the half through, we did this. Yeah, that's final answer. So this is the average value of the hyperbola over that given domain. It's the average y value. So like for instance, if f of x was an area equation, then what we just found was the average area for that domain. If it was a volume, then you would have found the average volume. So on and so forth. Anything to clarify further?
No.
That was a bit muffled. Was that an all good or?
But yeah, all good.
Yep. Okay. Question 7. Find antiderivative. Yeah. Okay. So if you have a look at the screen share, the question 7 one again, it's bringing up the hyperbola. How you have to every time they'll put a associated domain with the hyperbola, so you know whether you have to do a positive or negative version of that logarithm. Truncus is a little bit different. So truncus, only hyperbola goes to natural log. Every other type of thing where you have a power function type situation, so it's either power function in the bottom or power function on the top, that's always going to be the power law situation, x power of n, which is this one here. So that's just always going to be using that same rule there. And you'll notice because like even in the formula sheet, it'll say this only works where n does not equal -1. So basically, only works when not a hyperbola. Everything else works fine. Let's see. What's going on here? If f of 3 is -2, f dash of 3 is 5, find g dash of 3. Yeah, why not? It's got really nothing to do with calculus at all, but... Well, maybe it does. Yeah, let's find out. I'll start writing out the key information there. Maybe start having a think about what you might do.
Oh.
Alright, that's all written out. We want g dash of 3. We have f of 3 and f dash of 3. What could we do? A good hint with these would be to say, if I knew what f of x and g of x were just normally, how would I normally go about finding some random g dash of 3? Like if I had just said g of x equals x squared, and I said g dash of 3 of that, what are the steps you follow? That'll inform how you handle more complicated scenarios.
You would substitute like wherever x is at as 3. So in f of x, you would substitute it as like f of 3. Then
Kind of correct. Although, if you think about how you would do in a simpler example, like let's say g of x is x squared, if you had to find g dash of 3 in that situation, you don't sub 3 in first, you sub it in afterwards.
okay.
So you first do your g dash, which in this case would be 2x, and then you would plug in the 3. So you will absolutely plug those in, just not right now. So what that tells us is first step should be to figure out what g dash is. We can kind of do a lot of that already. Well, sorry, we can do all of it. Some of it's easier than others. What would g dash be?
Is it 6x?
6x is certainly part of it. Yeah. So you got 6x. But then you got to figure out how do I handle this part of the function. I got minus 5f of x.
So minus 5 f of x. So would you like make f of x just f dash of x?
Exactly right. Yeah.
And since like we know that f, like we're gonna like end up substituting like 3 into the thing,
hmm
and we already have f dash of 3 equal to 5, will that like help us find our answer?
I think so. We want g dash of 3. Yeah, these values will absolutely be important. This one, oddly enough, didn't seem to matter. But I guess it is a three-part question, so maybe... Yeah, it matters in the other ones, perhaps. Yeah, there's chain rule in the others, so this was where that would matter. This was a bit of a red herring for part A. But yeah, absolutely right. These values will be important. How do we use them? Or maybe even a better question than that. Instead of thinking, how do we use these, think, if I wanted to get g dash of 3 and didn't see any of this, what would my next line look like?
You substitute like x is 3.
Yeah, sub in x is 3. So if this was any other old g dash, then all I would do is put a 3 in all these spots. Then from there, once you've considered that, you'll start to see where those other points start to matter. Where do I go from here?
F dash 3 is equal to 5, so you would put 5 there in the brackets.
Yeah, precisely. F dash 3 is 5. So 5 is 25. 18 minus 25, and then that's math. 20, so that's minus 7. Yeah, I believe that's everything, right? We just want a g dash of 3. Yeah, we just want a g dash of 3. So, final answer, g dash of 3 equals minus 7. There's obviously a part B, part C there, but that just becomes slightly more complicated, where in part B, if you look at the screen share, that's going to be a chain rule situation. Sorry, not a chain rule, quotient rule, because you've got a division of two functions. And then part C, since you got function to power, that's a chain rule, because your f is u, and then it becomes u squared, and you go from there. Chain rule, quotient rule, both of those are going to require this f of 3 equals negative 2. So if you're curious to see how that goes, I'd encourage you to try one of those yourselves in your own time, though, because it is a very similar type of question. Same for 9. 9 is product rule, quotient rule, same sort of deal. F dash G. That's funny. Okay, we'll have a look at 10, if only because I don't know what what it's saying immediately. So let's spend some time deciphering it. I'll write down the key information while you have a read. Yeah, that's a weird one. So the goal is f dash. If you didn't know anything about g or little f dash, and you just had capital F of x is little f little g, how do you get f dash from that?
Wouldn't you antiderive like the f dash x equation?
Antiderive would not. So the dash notation is for derivative. It's a bit weird here because I've used a capital F for this. Usually you
Like I meant
use.
the lowercase f, like antiderive the lowercase f.
Oh, okay.
Yeah.
Yeah, so that's the next thing I was going to say, which is they've made it a bit confusing by using capital F and little f. Usually, capital F is the antidiff of little f, but in this case, it's defined a little bit differently, where they've said capital F is actually this composite function here. Now, antidiffing little f is still doable and still important, but it doesn't give you capital F, if that's what you meant.
Oh no, that's not what I meant.
Oh, okay, easy. But yeah, so yeah, anti-diffing little f, absolutely what we're going to do. That's going to give us little f of x is the anti-diff of... How do we handle roots? Anyone remember how we rewrite that a little bit?
Do we use the power of a half?
Power of a half, yeah, that's it. And so I'll just finish that one up. So raise the power becomes 3 over 2, 3x plus 4, and then it's 1 over 3 over 2, so 2 over 3. That's going to be our little f of x. There'll be a plus c, of course, which we might as well have it just in case we need it. Yep, so that's definitely a good first step. What else could we do from this? Oh, wait, hang on, this isn't even correct. This 3 here also has to be part of it, which means a further division of 3, which means 9 on that. There's a kind of chain rule for antidiff as well, where it's not just power at the front, but it's also this one.
Chris, since like it says f of g of x, right? Like that's what the capital F of x is.
Yep.
Do we need to now sub in x squared minus 1 into every x found on the small f of x?
Yeah, that sounds like a good idea to me. So yeah, for composite function, so we just go through capital F is therefore going to be 2 on 9, 3, and then instead of x we now have x squared minus 1. There's a plus 4, and there's a 3 over 2, and there's a plus c. We go through, simplify what's going on. Well, I say simplify, but it's still complicated. That's a minus 3 and a plus 4, which is going to make a plus 1. And that's going to give us capital F of x. But we don't quite want capital F of x, we want capital F dash of x, which we needed this. We absolutely needed it. What can we do now to finish this up?
Use chain rule.
Yes, this will be chain rule. Excellent. So, yeah, so we would take the u as this. So u equals 3x squared plus 1. U dash is 6x. Then capital F of u is therefore 2 on 9, u 3 on 2. Capital F dash of u is therefore, so 3 on 2 comes out the front, that's 3 on 9, that's 1 on 3, u half. And then, yeah, multiply those two things together. So you've got capital F dash of x is 6x out the front of, yeah, I'll just write it, 6x out the front of a third. The u was 3x squared. Yeah, u was 3x squared plus 1. And power half for, no, not that whole thing, just this one. Plus c at the front, doesn't matter what that constant was, derivative kills it. And yeah, just a little bit more simplifying. 6 over 3. And then you can rewrite this as a root. I'm going to put a tick there and pretend it was definitely correct and no room for error. I'm sure there might have been some weird thing there, but yeah, those are the overall steps that you follow. Nice. Nicely worked out. Alright, we did go a little bit over time there, so if you want to leave now, you can absolutely do so. Otherwise, if there's anything else to clarify, let me know. I'll hang around for a bit. Take care.
So I just have like one quick question.
Yeah, certainly.
Like, so like I find like face-to-face classes like a bit better. So is there any like possibility of like any face-to-face classes happening?
Well, where are you based?
Um, I'm like in Troganino. I live in Troganino.
Oh, you do live in Truganina. Huh, interesting. I mean, that does mean we are close by enough to potentially do that. Group classes though is going to be really tough to do in person, and so if you do like the in-person thing, it would be a private class situation if that's what you're looking for.
Um, I kind of prefer like as a group.
Yeah, I mean, fair enough. Um, but yeah, I would imagine pretty much no one here is anywhere close because Victoria quite wide, of course, and I pick students primarily online, so they could be anywhere. Yeah, there's, from what I remember, next to no one around here really, so it wouldn't really be a group thing, unfortunately.
Okay.
But yeah, if you
That's,
do like that one-on-one feeling and that, oh sorry, not the one-on-one, the in-person feeling, then yeah, I do recommend you start looking for that. Then, if that feels like it's more effective for you as far as your studies go. The resources here will still be available to you, and the class recordings will be available to you. So it's really just up to whatever you learn best from.
okay. Because like I feel that being like face to face, like you're gonna have that like extra interaction, and then like
Hmm.
you're gonna ask like like it's just easier to like communicate.
Yeah, well, absolutely, it is for sure. But it's also, yeah, very hard to set up. And so I don't know if I'll be able to do it while you're still in school, just building it up to the point where it could be in person like that. Um, but I would absolutely, once it gets to a point where I can reasonably do that, by all means, I would do that for as soon as possible, ideally. But I just looking at how it's progressing, I don't think it'll be while you're still in school. Um, but yeah, I would say if you're looking for that sort of in-person feel, there's definitely people that run things in libraries or stuff like that. It's going to be quite difficult to find a group in person unless you do like I don't know. Do you have a bunch of friends in school that want to do it or that are close by?
Um, no, not really.
Not really. Yeah, like that's like one of the ways you could do it. You could get friends together and just have study sessions, and then that becomes the group. That's the way I've found that model works best, right? Like from a tutor's perspective, it's really hard to round up a whole bunch of people that are nearby and do that. That are all in similar year levels without it being just like one person and a bunch of their friends, and then that starts the group. That's how it usually happens. Um, but yeah, all that to say, I don't think that'll be in the near future. More so because I have limited means rather than because I don't want to. Is the thing.
Okay, all right.
But yeah, so I guess I'll stand by it, which is I recommend you look for it if you feel like that'll be more effective for you. Um, and stuff will be here for you no matter what, pretty much.
All right. Okay. Thanks, sir.
No worries. I'll leave you to it.